This lecture introduces normal random variable and normal distribution. Normal random variable is the most commonly used continuous random variable. Before discussing normal random variables, we need first to discuss something about continuous random variable. Recall that a continuous random variable can take values in an interval. It has infinite possible number of values. On the contrary, a discrete random variable only takes values in a list. Usually, it has only finite number of values. For example, let x be the number of heads when tossing a balanced coin n times. You may still remember that x is a binomial random variable. The binomial random variable is a typical discrete random variable. When n equals 3, x has 4 possible values 0, 1, 2, 3. The probability histogram characterizes the distribution of x. Here, each bar corresponds to the probability of x at a certain value. Similarly, when n equals 10, x has 11 possible values. When n equals 50, x has 51 possible values. We can see that when n increases, the number of possible values of x also increases. The bar in the probability histogram becomes narrower. You can imagine that when n keep increasing, then x has infinite possible number of values. In this case, the shape of the histogram will become a smooth curve. The distribution of a continuous random variable is characterized by a smooth curve. This smooth curve is called the density curve of the continuous random variable. A density curve has some properties. Firstly, a density curve is always on or above the horizontal axis. It means that its value is 0 or positive and cannot be negative. It is similar to the probability distribution of a discrete random variable. Its value is non-negative. Secondly, the total area under a density curve is 1. Recall that for a discrete random variable, the sum of its probabilities equals 1. Here, the sum of probabilities becomes the area under the curve. The area under the density curve equals 1. We will use the density curve of a continuous random variable to calculate probability, or percentage involving a random variable. Let x be a continuous random variable. We may need to calculate the probability less than a value, larger than a value, or between two values. The graphs on the slide demonstrate these three scenarios. We can see that the probability corresponds to the area of shaded regions under the density curve. The probability of x less than or equal to a value c is the area to the left of c. The probability of x larger than or equal to d is the area to the right of d. The probability of x between two values, a and b, is the area between a and b. Notice that the total area under the curve is 1. The shaded region only covers a portion of the region under the curve. Therefore, the corresponding probability is less than 1. This slide tells us that to find a probability of a continuous random variable, we just need to find the area of the corresponding region. Let's look at an example. The crystals of a certain mineral are cubes. The length of the sides has the density curve y equals x over 2. Here, the length takes values in the interval from 0 to 2. We want to calculate some probabilities. What is the percentage of these crystals that have side lengths less than 0.5 millimeters? In this case, we need to find the area to the left of 0.5. From the graph, we can see that the area under the density curve is a triangle. To calculate the area of a triangle, we just need to calculate the product of base and height and then divide it by 2. In the graph, the base is 0.5. The height is the value of y, or y equals x over 2. So the height is 0.5 over 2 equals 0.25. The area of the triangle is therefore 0.5 times 0.25 divided by 2 equals 0.0625. The percentage of these crystals that have side lengths less than 0.5 millimeters is 0.0625. What is the percentage of these crystals that have side lengths between 1 millimeter and 1.5 millimeter? In this problem, we need to find the area between two values, 1 and 1.5. The area under the density curve is trapezoid. To calculate the area of a trapezoid, we calculate the sum of two bases, multiply it by the height, and then divide it by 2. Notice that the length of two bases are the value of y at x equals 1 and x equal to 1.5. The values of x and y are connected by the function y equals x over 2. Therefore, the length of bases are 0.5 and 0.75. Their sum is 0.5 plus 0.75 equals 1.25. The height of the trapezoid is 0.5. Therefore, the area is 1.25 times 0.5 over 2 equals 0.3125. The percentage of these crystals that have side lengths between 1 millimeter and 1.5 millimeter is 0.3125. What is the percentage of these crystals that have side lengths at least 0.25? In this problem, we need to find the probability to the right of 0.25. The shaded region is also a trapezoid. The length of two bases are 0.25 over 2 equals 0.125 and 2 over 2 equals 1. The height is 2 minus 0.025. 2 minus 0.25 equals 1.75. Therefore, the area of the trapezoid is 0.125 plus 1 times 1.75 over 2 equals 0.984375. The percentage of these crystals that have side lengths at least 0.25 is 0.984375. Using this example, we demonstrate how to calculate the probability of a continuous random variable. In many cases, the density curve of a continuous random variable can be expressed as a function f of x. For example, in the previous example, the density function is x over 2. Of course, in practice, a density function is usually much more complicated. The cumulative distribution function of a continuous random variable is the probability less than or equal to a value. Consider the example we just discussed. The probability less than or equal to x is just the area of a triangle. We can calculate the area easily, which is x squared over 4. If you are familiar with calculus, you may recall that the calculation of the area under a curve is exactly to integrate the corresponding function. Formally, the cumulative distribution function is exactly the integral of density function. Using calculus, we can also calculate the area to the shaded region, which equals x squared over 4. Don't worry about calculus. We will not use calculus in this course. Here, I just want to draw a connection between cumulative distribution function and integral. If you need to take more advanced courses on probability and statistics, this connection is important. The probability of a continuous random variable can be represented in terms of cumulative distribution. For example, if you want to know the probability between two values a and b, it is enough to calculate the cumulative distribution at these two values and then calculate their difference. Here, I want to mention a striking difference between continuous random variable and a discrete random variable. For a continuous random variable, the probability that x equals to a single value a is always 0. Recall that the probability of a continuous random variable is the area under the density curve. A single value corresponds to a vertical line segment under the curve. A line segment has no area, therefore, its probability is 0. This property makes the calculation of probabilities for continuous random variables quite different from discrete random variables. For example, in the bottom of this slide, I list 4 probabilities. The difference is that some have equal signs and some do not. However, they are all equal. Recall that we have discussed many examples for discrete random variables. These probabilities are usually unequal for discrete random variables. A variable is said to be a normally distributed variable or to have a normal distribution if its distribution has the shape of a normal curve. A normal curve is a symmetric and bell-shaped curve. More rigorously, a normal curve can be expressed in terms of the following function. The value pi in the denominator is a constant. It is approximately 3.14, which is exactly the constant you use to calculate the area of a circle. Notice that this function has 2 parameters, mu and sigma. The parameter mu is exactly the mean of normal distribution. The parameter sigma is the standard deviation. In the slide, I show you some density curves with different values of mu and sigma. You can see that a normal curve is centered at mu and it is symmetric about mu. Therefore, we may see that mu determines the center of the distribution. If we increase the value of mu, the density curve will move towards the right. If we decrease the value of mu, the density curve will move towards the left. The parameter sigma determines the shape of the distribution. The larger the value of sigma is, the flatter the shape is. In this case, the distribution spreads much wider. The smaller the value of sigma is, the distribution concentrated more around its center. We have a special normal distribution called standard normal distribution. Its mean is 0 and the standard deviation is 1. If we replace mu by 0 and sigma by 1 in the density function of normal, we get the standard normal curve. Any normal random variable can be standardized to have mean 0 and standard deviation 1. If we subtract a normal random variable by its mean and divide it by its standard deviation, the resulting random variable is a standardized normal random variable. This graph demonstrates the process of standardization. The 3 curves have different means and standard deviations. After standardization, they become the same normal random variable with mean 0 and standard deviation 1. We will do standardization frequently when calculating the probabilities of a random variable. For example, to find the percentage of a normal random variable between 2 values, we will usually first do standardization. Equivalently, we calculate the z-score of the value a and b, then determine the corresponding area under the curve in terms of the standard normal random variable, which gives us the answer. You may ask why we bother to do standardization. Recall that the normal density function has complicated expressions. We cannot calculate the probability under the curve by hand. Therefore, we need the help of computers. If we standardize all different normal random variables to a common one, we can construct a table that lists the probabilities for this standard normal random variable. Therefore, we can calculate the probability of normal random variable using such a table. This approach is the only choice in old days. Right now, even computers are convenient and easy to access. Such a table is still commonly used in applications.